Alrighty. So here's what happened in this chapter, chapter 9. First, we dealt with polynomial approximations. We dealt with Taylor polynomials and Maclaurin polynomials. You were able to get polynomial approximations, polynomial approximations for sine of x, cosine of x, e to the x, stuff like that, okay? Then we took a little detour and learned a whole bunch about series, about convergence of series. Well, now, believe it or not, we're going to put those two things together. We're going to put that Taylor polynomial type stuff and convergence of series stuff together and bring it all together with convergence of power series. And that's what we're learning. So let me show you what a power series is, and then we'll start working with these power series. And I want to say again, just like before, our goal is always to, with Taylor and Maclaurin, we were approximating weird functions with polynomial equations, but now we're not really approximating weird functions with polynomial equations. We just got the polynomial equation, and the polynomial equation will often be kind of weird. But now we're just dealing with polynomial equations. We're not going to be doing the Taylor and Maclaurin. I mean, we are going to be doing that, but this is like more. This is power series on their own terms. So here, let me just define for you what a power series is. A power series is a function, f of x, but it's going to be an infinite polynomial. As n goes from 0 to infinity of a sub n times x to the n, that's a power series. That's a polynomial function with an infinite number of terms. And those coefficients are given by the sequence a sub n. So if I wanted to write this out, this would be a naught plus a1x plus a2x squared plus a3x to the third plus dot, 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 forever and ever and ever. An infinite polynomial. Now, this particular polynomial is centered at 0. Centered at x equals 0. Because it turns out we're going to find that with this infinite polynomial, there's going to be some values that we can plug in where you get a finite answer, and values that you plug in where you get an infinite answer. And so where it's centered is going to tell us, okay, those range of values where I can plug in a number and get a finite answer, those range of values end up being centered at the center of the power series. And you'll see more of that as we go. There's another version of the power series. It's just a function. It's the sum as n goes from 0 to infinity, a sub n times x minus c to the n power. And this, as you can imagine, is a power series centered at x equals c. So this ends up being a naught plus a1 times x minus c plus a2 times x minus c squared plus dot, dot, dot. Just parenthetically, as a reminder, do you guys remember with Taylor and Maclaurin polynomials what a naught, a1, a2, a3, etc.? Do you remember what those guys were equal to? Was it Taylor? What's that?
Each of the derivatives.
Okay, well, be more specific. What's a naught equal to?
The first term. No, the function.
Yeah, the functional value evaluated where?
At C.
Yeah, at C. Do you remember that? Where a for these power series, if it's going to be Taylor or Maclaurin, although Maclaurin it's centered at 1, but Taylor or Maclaurin, this ends up being f of c, f prime of c, f double prime of c over 2 factorial, f triple prime of c over 3 factorial, etc. Okay? So essentially what we learned, 2 weeks ago was power series with a very specific, a naught, a1, a2, a3. Very specific. It was that and none other. But now we're going to expand our experience with power series and say, hey, this series, this sequence of coefficients can be anything we want in the world. It doesn't specifically have to be Taylor and Maclaurin, polynomial coefficients. It can be anything we want. And so that's what's going to happen. Okay, great. So here's the thing. You're adding up an infinite number of terms, and so you know what's the most likely answer you're going to get when you add up an infinite number of terms?
Infinity.
Yeah, infinity, right? I mean, more often than not, you add up an infinite number of things, you're going to get infinity. But sometimes you'll add up an infinite number of terms and get a finite answer. We use the term convergence. This thing will converge if you can stick in some value of x so that you're adding up an infinite number of terms and the thing still converges, okay? And so let's define again what our interval of convergence is. It just bears repeating. The interval of convergence is those values of x that you can plug in such that you get a finite answer. Those values of x that you can plug in to an infinite power series that gives, or yields, I guess, I'll say gives, a finite answer. Sometimes getting the interval of convergence is really, really easy. Let me give you an example. This is one where you can actually just use your cleverness. Suppose my sequence A sub n was just equal to 1. That is, suppose I had a sequence. Am I going to run out of time? Okay, good. So suppose I have a sequence where every single term, every single coefficient is just 1. 1, 1, 1, 1, 1, 1, 1. So my power series f of x is going to be the sum as n goes from 0 to infinity of 1 times x to the n. Oh, let's suppose it's centered at 0. That is, this is going to be 1 plus x squared plus x to the third plus x to the fourth plus dot, dot, dot. I wonder if anyone can tell me, what would my interval of convergence be here? What are the values of x that I can plug in so that I'm going to get a finite answer at the end when I add up this infinity of terms? Okay, 0. Good, 0. You can plug 0 in, and you're going to get a finite answer. It's 1. Are there any other numbers I can plug in besides 0?
1.
Okay. Okay, say that again?
1/2.
Good. You guys okay? I can plug in a half. Because then I got a 1 plus a half plus a fourth plus an eighth plus a 16th, and you know that adds up to 2.
7/8.
Good. I can plug in 7/8, right? So now, can I plug in negative a half?
Yeah.
Sure. In fact, now you're ready to tell me, what's my interval of convergence?
Negative 1 to 1.
Yeah, negative 1 to 1, right?
But it cannot-
That's my interval of convergence. Interval of convergence is going to be negative 1 to 1, right? And you guys got that just by using your cleverness. You didn't have to use any weird techniques. You just use your cleverness and determined, okay, this power series is going to converge for any value of x I plug in between negative 1 and 1. But it's going to diverge if I stick in a 1. Because if I stick in a 1, I get 1 plus 1 plus 1 plus 1 plus 1, which is infinity. If I stick in a negative 1, I get 1 minus 1 plus 1 minus 1 plus 1 minus 1, which doesn't equal infinity, but it has no particular answer, right? You don't know whether the answer is positive 1 or 0, depending on when you stop. So you can't plug in negative 1 and get a finite answer, a particular finite answer. You can't plug in 1 and get a finite answer. You get infinity, and so that's your interval of convergence, okay? Here, what if I gave you another one? What if I gave you f of x equals the sum as n goes from 0 to infinity of 1? So I'm still going to use a sub n as 1, but now this is going to be x minus 2 to the n power. That is, this is going to be 1 plus x minus 2 plus x minus 2 squared plus x minus 2 to the third power plus dot dot dot. Can you use your cleverness and get your interval of convergence there?
Yes. Yeah.
Okay, can you plug in 2?
No. Yeah, yes.
Yeah, it's centered at 2, right? You guys okay? It's centered at 2. I plug in 2, I just get 1.
Yeah.
So what's the interval? Carly, I'm just getting this vibe that you know the answer. What's the interval of convergence going to be? Okay, I knew it. I just knew it. It's a weird thing. It's like when I walk in the house and I did something really embarrassing and bad, and I just take one look at my wife and I know she knows. You know? Oh, anyway. Sure. I shouldn't say that. That never happens.
Does it happen on a regular basis?
No. But I mean, the sort of stuff she gets mad about is like when I clean up, which means what I do is just disorder everything. Because she has chaos, but it's a very knowable chaos.
Yeah.
Then when I clean up, no, she can't find anything. I don't know. Okay, great. So interval of convergence, as Carly says, it's going to be 1 to 3. And again, you know, she just used her cleverness. She didn't use any techniques. But you know, power series don't get any easier than a sub n equaling 1. Power series get way more complicated than that. And so we're going to learn today, number 1, for my interval of convergence, there ends up actually being only 3 possible choices for the interval of convergence. Okay, that's the first thing you're going to learn, and that's going to be between today and our next time together. And we're going to find that, you know, in situations where you can't use your cleverness, we're going to apply the ratio test to find the interval of convergence. And then finally, since the ratio test doesn't work when the ratio is actually exactly equal to 1, we're going to find that we're going to have to check the endpoints. Here, I don't have to, I mean, here we are checking the endpoints, right? You stick in 3 and I get 1 plus 1 plus 1 plus 1, so you know 3 doesn't work. I stick in 1, I get 1 minus 1 plus 1 minus 1, so you know 1 doesn't work. But there's going to be some times when one or both of the endpoints actually works. You're going to stick in 3 and you're going to get a convergent series. You see it? So we're going to have to check the endpoints. Okay, hey, I'm going to tell you the 3 choices, and we'll see how far we go. Like I said earlier in the class, you know, our homework assignment doesn't involve any of the stuff you're learning now. So I'm kind of really taking my time with the introduction in the hopes that this will make a lot of sense to you before you start just doing ratio test and doing all the algebra and playing with numbers and symbols. Okay, great. 3 possibilities for the interval of convergence. And this is for any power series, whether the power series is complicated or incredibly simple like that one. There's only 3 possibilities for the interval of convergence. The first possibility, there's actually power series I can give you where it converges only at the center of the power series. So let me see here. F of x is finite only at x equals c. Let me give you an incredibly easy example of this. The sum, as n goes from 0 to infinity, of n factorial times x. So that I end up getting 1 plus x plus 2x squared plus 6x to the third plus 24x to the fourth plus dot dot dot. This converges for x equals 0, right? You stick in a 0, you get 1. But any other x you put in, you're going to get infinity. Because even if you put in an x of 0.01, right? 0.01, 0.01 squared, 0.01 to the third, 0.01 to the fourth, that coefficient, since it's n factorial, and n factorial is infinitely bigger than just n, you know, or n to the, or I'm sorry, any number to the n power, you know, because n factorial is infinitely bigger than any number to the n power, no matter what that number is. Pretty soon, my 0.01 to the 12th power is being swamped by 12 factorial. And 0.01 to the 20th power is going to be completely destroyed by 20 factorial, which is a huge number, you see? So in this case, any number I plug in for x is going to give me infinity, except specifically 0. So this is an example of a power series where it's kind of a worthless power series. I can plug in 0 and get 1, and I plug in anything else, I get infinity. Well, what use is that? So that's one possibility. The second possibility is f of x converges for all values of x. That is, the interval of convergence is negative infinity is less than x, which is less than infinity. So there's some incredibly convenient power series where you can plug in any value of x you want, and you're going to get something that's finite. An example of that is e to the x, you know? I just want to remind you, e to the x ends up equaling the sum as n goes from 0 to infinity of 1 over n factorial times x. That's e to the x. You know, 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. Because e to the x and all the derivatives are e to the x, so f of 0 and all the derivatives, f prime of 0, f double prime of 0, are all 1. You know, this ends up being 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. Blah, blah, blah. Now, I can plug in any value of x I want, and I'm going to get a finite answer. So f of x converges for all values of x. Even if I put in a million billion for x, I add up an infinite number of terms. Pretty soon, you know, a million billion to the 30th power is way, way, way less than 30 factorial, you know? So these guys converge, okay? And then the third choice, which is what we did with example 1, what we found with example 1, is this. F of x is, you know, finite for only a range of x. And that range could be x is between a and b, but not including a and b, or x is between a and b, but includes both a and b, or just one of the endpoints work. And you're going to have to decide which of these 4 it is by checking the endpoints, which I'll teach you about on Tuesday. Yes, Tuesday, because our quiz is Wednesday. Yeah. So that's it. I'm going to essentially stop now, and on Tuesday we'll start applying the ratio test to these power series, and then we'll check the endpoints, and then that's it, man. That's pretty much chapter 9. So, any questions or issues? Okay, bye-bye.